Hello everyone, welcome to this session. So in this session, we will talk about the GA crossover and mutation. So as we can see from the GA workflow, we have already discussed the initialization and the selection. So in this session, we will focus on this, crossover and mutation. So let's start from crossover. As I have said, crossover and mutation have the same purpose, and that is what? To generate new solutions. So these operations have some common characteristics. So first of all, they act directly on the individuals. So we can come somewhere and swap some strings, right? So act on directly on the individuals. And often they happen after the selection. So crossover happens to the mating pool and mutation happens to the child solution after crossover, right? In most cases, these operators has nothing to do with fitness, but because the fitness doesn't involve in these operators. So these are the common characteristics of crossover and mutation. So in crossover, what we do is that we have two individuals and we cross over with each other in a certain way, right? So in the example, what we show is how we call it the simple crossover, or we call it a one-point crossover. Recall that before crossover, two individuals could be like that. So we select here, we call it the crossover site. So after crossover, we can see this part remains, this part swap. Right? So this is single point crossover. And later we will talk about key point crossover following the similar way. So let's see the single point crossover first. So we can summarize the single point crossover in 3 steps. So step 1, we randomly select two individuals from the mating pool. In this step, we have 2 parent solutions. Then we will also, the next step, to randomly select a crossover site. And the third step, we swapping to generate 2 child solutions. Let's see an example. For example, the randomly selected crossover site is 4. Then for the 2 parents, we cut here, and for the 2 child solution, we remain this part and swap this part. Right? We can see that. So for key point crossover, this is different. So the difference is that not only one crossover site, this time we could have a key crossover site. So in one case, maybe we say we have 2 crossover sites, and then we can what? We can make the front and end the same and swap the substrings in the middle. So let's see an example. So k equals to 2 crossover site. With this time we randomly select 2. One is the second, one is the fourth. So we can see here and here, we put 2 bars. We remain the front and the end, and we swap in the middle. So if you want to remain in the middle and swap the front and the end, that's also okay. Right. So this is the procedure of crossover. For the next step, I will introduce a new concept. We call it crossover rate. So crossover rate means what? Means not in all the cases crossover happen. So it has a rate. So we call it PC. So the 2 parents from the mating pool undergo crossover with a probability PC. To implement this, what we can do is that we generate a random number, we call it RC, between 0 and 1. Then I will compare it with PC. If the RC is smaller than or equal to PC, then we do crossover to these 2 parent solutions and generate 2 child solutions with crossover. So otherwise, we don't do crossover, and the 2 parent solutions themselves will become the offspring solutions. Later I will show you an example. So normally we want to promote the crossover, so the PC is often high. So PC is often from 60% to 90%. Okay, so now this is example. So we can consider the mating pool. We select 2 of them. Now we consider generate the RC, compare with PC. Okay, smaller than PC, we do crossover. Crossover site is 2. We put it here, then we do the crossover. Well, for the next one, the RC is larger than PC. So in this way, we don't do crossover. As you can see, this one just becomes the child solution. This one also directly become the child solution. But then we need to think of the effect of a crossover. So if we have a finite set of individuals, for some of them, after we do the crossover, it may increase the fitness. For some others, it may decrease the fitness. So consider we have an infinite set of individuals. So while we act the crossover, the average fitness should not change. So this is because the crossover we acted directly on the individual, and the fitness is not involved in this operation. And also the crossover increases the diversity. As we can see here, we have 3 different individuals before crossover, because we can see the 56, these two are the same, right? And after the crossover, there are 4 different ones. So the crossover increases diversity. However, in some cases, if we only use crossover, it may not guarantee to generate new individuals. So for example, let's see this example. You can see that using this example, no matter how you cross, how you change, how you swap, you can't generate new solutions. So let's see an example. If we cross here from the first 2, we can see we swap them, they become the same thing. The latter 2, if we cut here, they become the same thing also. So in this case, only crossover doesn't work. So in this way, we have to introduce an operator, and that is mutation. So after the crossover, a gene mutation occurs in one of the individuals, which is happened in our examples. So for mutation, we have several principles. So first of all, different from crossover, the mutation rate or the probability to mutation should be small. So normally this is 1% to 0.1%. And there are many ways to do the mutation according to different kinds of problems. So if it's a binary string, this is quite simple. We change 0 to 1 or change 1 to 0. And mutation, this is guaranteed to generate new individuals, right? So I do show the implementation of mutation in binary strings because it's very straightforward. Okay, so that's all for this session. Thank you very much. Bye-bye.